Hi, everybody. Welcome to the first installation of the Spectral Geometry in the Cloud seminar for 2025. So for the talk today, we have Rupert Frank, who will tell us about asymptotic optimization of Riesz means of Laplace eigenvalues on convex sets. And as usual, if you have questions during the talk, don't hesitate to unmute yourself or ask questions in the chat and we'll relay them. Rupert, the floor is yours.
All right. Well, thanks a lot for the invitation. I very much enjoy this seminar. Thanks for organizing this and for continuing to organize this. This is great. As you already said, this is about shape optimization problem, spectral shape optimization problem, and more precisely, its asymptotic aspects. Everything I'm saying is joint work with Simon Larson, from whom I learned this problem. I think he had a paper some 10 years ago on this, and he had some very important initial ideas of how to deal with this. And then the main focus of today will be 3 papers that are down there, where we sort of expand on these ideas. It's somewhat lengthy. I mean, these 3 papers together are something like 200 or 220 pages. And so which might look a bit scary, but I'll try to, emphasize the main aspects and perhaps give you a guidance where you find these things. And as Sean already said, if you have any questions, then please feel free to stop me. That's what I'm here for. All right. So here's the setup. So we are in Euclidean space RD. D is the dimension. D will typically be 2 or larger. The one-dimensional case is not interesting. And then we look at either the Dirichlet or the Neumann Laplacian on this set. And a priori, we define them just using quadratic forms. And then what we will do is we look at these Riesz means. Okay, and they depend on a certain number gamma, which is the Riesz exponent. And what you immediately should have in mind is sort of the smaller gamma, the harder the problem is. But also the richer it is. And it's perhaps to understand these Riesz means, it's perhaps easiest to look at the situation, which is the only situation that we're interested in, is that this operator has discrete spectrum. And then what this trace means is simply you take these eigenvalues, of course, repeated according to multiplicities, you subtract this cutoff energy or capital lambda, and then you take the negative part of this, meaning you throw away all eigenvalues that are larger than this cutoff capital lambda, and then you raise the corresponding thing to the power gamma. Okay? So this is a standard quantity that people have studied in eigenvalue asymptotic theorems. The literature from the 50s or 60s is full of those Riesz means. For some reason, then they have disappeared in the eigenvalue asymptotic literature. They came back a little bit in the work of Lieb-Thiering about Schrödinger eigenvalues. And well, our works with Simon have sort of focused on these Riesz means. Of course, sort of the limiting case, gamma equal to 0, in that case, this simply becomes the counting function of all eigenvalues below this capital lambda. This is also of great interest, and we would be very happy to deal with that case. We cannot at the moment, or we don't have any definite results about that in the moment, but at least, as you will see, by now we can deal with any gamma all the way down to 0, just excluding the endpoint case. And I should also emphasize that the case gamma equal to 1 is of particular significance in physics. So perhaps from a physics point of view, that is actually the most important case, gamma equal to 1. Anyway, so what do we do with these Riesz means? I'm told you we will look at a shape optimization problem. And the problem is that we will try to optimize these Riesz means. By optimize, I mean either make them as large as possible or as small as possible. Among what? Among all convex sets of volume 1. All right. I'll talk a little bit later about the convexity. The volume normalization, I mean, you can just normalize this to any given value because you have a scaling relation because of this capital lambda parameter. And so we use the capital lambda as the asymptotic, the parameter that we will play with. And on the other hand, the volume will be fixed to 1. That's a normalization. Okay. Now, the convexity, well, of course, one would like to study this problem without convexity, but yet again, I mean, this is too hard for us at the moment. We are happy to say something about the convex case. One has to start somewhere. And well, we can now, you will see, there's some things that we can say that we're happy with, other things that we still cannot say. And so if we cannot even say them, these latter things in the convex case, then there's perhaps no reason to look at other things. I don't think convexity per se is really the important thing, but it is a certain class where you have some regularity or some control on what the sets could do. What would certainly work is also if you go to subclasses of convex sets. So for instance, in 2 dimensions, you could look at convex polygons with at most n sides, and you could study similar problems in such subclasses. But I mean, for simplicity, I want to go to the set where we optimize with respect to convex sets. All right. Now, the next thing was this issue about what does optimization mean? And so we all know the Faber-Cran inequality is the example. Dirichlet eigenvalues we want to minimize, whereas Neumann eigenvalues we want to maximize. And the opposite problems are trivial. All right. And now that's the same thing we do here. It's just because there's this negative part, you know, this switches the sign. So in the Dirichlet case, we do a supremum, but we should remember that this is really minimizing eigenvalues. And in the Neumann case, we do an infimum, again, remembering that the eigenvalues we maximize. So these are the 2 natural optimization problems. That makes sense. Now, the next thing I want to talk about is the role of this parameter lambda. So I've defined this optimization problem for each given cutoff parameter lambda. Or if you want, you could put this equal to 1 and change the normalization. It's the same. But what we are interested in is an asymptotic result when lambda goes to infinity. Okay, and so we try to say something about this. I mean, you know, if you're very optimistic, you might say, I told you, well, Faber-Cran, well, this shape optimization problem, that gives you a ball. Okay, so I think it is not true that the solution to these problems always is a ball. I think that's numerically is just plain wrong. But we hope that we can say something in an asymptotic regime, namely where this parameter lambda goes to infinity. I was before already telling you that these Riesz parameters were natural, but perhaps are less natural these days. So let me perhaps talk about a different problem, which is essentially equivalent. By essentially equivalent, I don't want to be very precise, but there are very strong analogies, and I would imagine that whatever we do has an analogy for this other problem. So what is this other problem? So there you look at partial sums of eigenvalue powers. So you choose a power p, okay, take the lowest capital N eigenvalues either with Dirichlet or with Neumann, and then you minimize this or maximize this, depending on whether you're Dirichlet or Neumann. Okay, and so what I'm saying is that this problem is very closely related to that problem. For when gamma is equal to 1, then p is equal to 1, and they're actually the same. I mean, really honestly the same. Now, the this problem, I told you the difficulty is to consider small gammas. And you see that here, because if you look at small gammas, that roughly corresponds to taking very, very large p. And so as p goes to infinity, this will become an L infinity norm, meaning what is the largest eigenvalue? Well, that's the nth, the capital Nth eigenvalue. So in the limit, we sort of look at the problem as of minimizing the nth Dirichlet eigenvalue or as maximizing the nth Neumann eigenvalue. As I said, we don't really do this, but you can think that this P or our gamma gives us a small regularization of this limiting problem. And then what is the asymptotic regime? We take lambda to infinity, whereas in this problem where you have partial eigenvalue sums, we take capital N to infinity. This is the relation. And now you might ask me, why do I insist on that formulation with the Riesz means instead of the partial sums? Well, the point is sort of I have more locality in the problem. And this is best seen in sort of Weyl asymptotics, where the coefficient in the Weyl asymptotics of this trace becomes the volume. So sort of a trace becomes a volume. And sort of then you can think of localizing the trace. And so sort of half the trace becomes half the volume or something like this if you live in two different regions. Whereas if you look at these partial sums, then the leading term in Weyl's law is a certain power of omega, and then localizations are not so easy anymore. So that's the chief reason why we look at this. But if you're really interested in this, one might be able to translate things. Okay, that was the setting of the problem. So what do we expect in this regime where capital lambda tends to infinity? The buzzword here is Weyl asymptotics. Okay, this means that these two traces have a certain power-like asymptotic as you go to infinity. The first term is this Weyl term, the main term, which is proportional to the volume times a certain power of lambda. There's always a constant in front, which will appear and appear throughout the talk. Just ignore it for the moment. This has a certain explicit expression in terms of gamma functions, has also some meanings, but it plays a smaller role. Now, what's relevant for us in this connection is a second term in these asymptotics. Now, having a second term for gamma equal to 0 typically requires extra condition. When gamma is positive, it does not. And we have a second term, which is negative for Dirichlet and positive for Neumann. And the second term is proportional to the surface area. Okay, good. So now let's, just to get a little bit of an idea about this optimization problem, let's pretend for the moment that these asymptotics would be uniform among all convex set of measure 1. Okay? Then what do? Remember, we want to make this, in the Dirichlet case, we want to make this Riesz mean as large as possible among sets of fixed measure. So because of that minus sign, we want to make this term, right? The first term is a constant. We have a volume normalization, so this term drops out. The first term you can forget. So really everything is about the second term and taking the sign into account. Making this thing as large as possible means making the surface area as small as possible among all sets of equal volume. Same thing for Neumann. There we want to make this thing as large as possible, as small as possible. So this means because of the plus sign, we want to make the surface area again as small as possible under volume constraint. So if you believe this, there's this very big if you had this uniformity, that you could interchange the asymptotic with the min and the max. If you could do that, then you would arrive at the problem of minimizing surface area with respect to volume. That's the isoperimetric problem. Well, we still have the convexity constraint, but that makes the problem only easier. The solution of the isoperimetric problem of course, is the ball. So from this, all these big ifs, you might arrive at the conjecture that the optimizers of our shape optimization problems should converge to balls as lambda goes to infinity. That's the big conjecture. That's what we want to prove. And that's essentially what the main result tells us. So even though this if is really wrong, I mean, these asymptotics are not uniform, the conjecture we arrived at holds at least under certain assumptions. And so the assumptions are as follows. So the results are equally valid for Dirichlet and for Neumann. Doesn't matter which. In 2 dimensions, you don't have any restriction. You can take any Riesz mean all the way down to gamma equal to 0. When the dimension is 3 or higher, then there is a restriction. You need the Riesz parameter at least somewhat positive, but it's greater or equal than 1/2. And in particular, it includes the physical case of gamma equal to 1. Okay, now the result is that these optimizers of our shape optimization problem converge to a ball of unit measure, and they do so in the strongest possible sense, or the strongest sense you can imagine, namely in Hausdorff, with respect to the Hausdorff metric. Okay, so that's the result we can prove. And actually, we have this theorem holds not only for minimizers or for optimizers of our problem. This word optimizers really should mean, instead of minimizers here, I should say optimizers. It holds for a much more general sequence of sets, namely sets that optimize our Riesz mean up to this order that's hidden in this little O term, right? So of course, I mean, minimizers minimize it up to every order, but the point that I'm trying to tell you is we are not, we do not use optimality conditions. We never say that the set is a minimizer, therefore it satisfies an Euler-Lagrange equation, whatever that may be, and then we get something from that. It's a purely energetic assumption on our sets. If the sets have energies close to the optimal energy, then we have convergence to balls. It's a stronger conclusion. Okay? So that's the first main result. But it sort of has this drawback that in dimension 3, we have this extra condition. A gamma's got to be greater than 1/2. And so that prompted us to further investigate this. And then the problem actually becomes quite interesting. So let me come here. This is the full version of the result. And if you skip over the upper part of the slide, you see, well, it's very similar. We again have lambdas and omegas, and we again have the almost optimality condition. And the conclusion is again that we converge in Hausdorff sense to a unit measure ball. Right, I abbreviated here up to translations because our sets can live anywhere, but that you can ignore. Okay, so that's the conclusion we want to get. And that here we have the same conclusion. However, you see from the slide that there is another part of the theorem where the conclusion is different, where we do not converge to a ball. So let me explain you this additional part, because that's the part that will be relevant in dimension D for small values of gamma. Okay, here's how it goes. I want to look at such inequalities where I have Riesz means on the left, and on the right, I have, well, the same expression, right, that I see in my Weyl law, except I don't know whether you see, this was the Weyl law, the first term in the Weyl law. In the Weyl law, I have a very specific constant there, which I write SC for semiclassical. Now, I don't know whether that constant, the Weyl law, gives me such a bound. So I call the best constant, the smallest possible constant I can put there in the Dirichlet case, I call it by L gamma D, and then a D upstairs for Dirichlet. Similarly, in the Neumann case, I put a capital N here, and now the constant is as large as I can do. And I want this inequality to hold for all lambda, and for all convex bounded open sets. Okay, that's a definition. I mean, it's not hard to see that there is such a constant. It exists. Depends on gamma and d and your choice of boundary conditions. But let's give it a name. Let's call it L, gamma d, and then Dirichlet or Neumann upstairs. Now, of course, the constant that I would like to put there would be the semiclassical constant, right? So I would like to prove that the first term in the Weyl asymptotics provides a uniform bound for Dirichlet and for Neumann eigenvalues. That is true if my Riesz exponent is 1 or larger, right? Large Riesz exponents sort of make life easier. Could also be that it's true for smaller values of gamma. Actually, that's what Polya conjectured, right? Polya conjectured that here I can put the semiclassical constant for all values of gamma all the way down to gamma equal to 0. Polya conjectured this even for general sets, no necessity to put convex. But I'm more modest. I'm happy if this holds for convex sets. Anyway, so what I was telling you is for gamma greater or equal than 1, you can put the semiclassical constant. And then there's an argument by Eisenman and Lieb, which says that if for some number gamma, no matter which, you can put the semiclassical constant, then afterwards you can always put the semiclassical constant. Okay? So what that means is I get a critical Riesz exponent, which I call gamma d, and then this hashtag standing for either Dirichlet or Neumann. And this is the critical value above which I have the semiclassical constant and below which I do not have the semiclassical constant. Okay? I need that number. I need that critical exponent. And if we believe Polya, then this critical exponent is 0, and the second part of my theorem is void. But if this critical exponent is not 0, but instead is large, and by large I mean greater than 1/2, then two cases can arise. Namely, now I start seeing a difference between big values of gamma and small values of gamma. Okay? When gamma is relatively big, then as before, I have convergence to a unit measure ball. If gamma is relatively small, then my optimizers do not converge to balls. So then these heuristics on the previous slides are all wrong. They degenerate in a spaghetti-like fashion. What do I mean by this? By this, I mean these are convex sets, and I mean that they become elongated in exactly one direction. In the orthogonal d-1 directions, they remain of size 1. I mean, not size 1 because they're volume normalized, but such that the volume is fine. What I mean is that the ratio between all the other directions is the same, is comparable. Okay, it's a set which has one long direction and d-1 comparable directions. Okay, that's degenerates in spaghetti-like fashion. I think really of a long spaghetti that's super long in one way. The spaghetti has a cross section. I don't know what the cross section is, but it's a set in d-1 dimensions. Okay, and so this is what's happening. Okay, so I mean this is if it turns out that this critical exponent is strictly bigger than 1/2, then you can choose a certain gamma for which you do not have convergence to balls. So there's really something going on. If, of course, this happens. Okay, and also I want to point out we can compute the energy, I mean the value of our optimization problem. And it turns out that this value, see, that's the value that I would normally get. That's the one I had if my heuristics before was true. I would get the semiclassical constant times the appropriate power of lambda. But then I get a prefactor in the bad case, which may or may not happen. I get a prefactor, and the prefactor is different from 1. Okay, at least if this inequality is strict. All right. So really, it's not only I have the degeneration of optimizers, I also have the even to leading order, to this order here, my heuristics was wrong. Okay. So let me, this is the same theorem, just written it down for you to stare at it some more. I want to emphasize that this critical exponent, right? That's the one where in this inequality we see the change between semiclassical and non-semiclassical behavior. That this critical exponent appears with index d minus 1. It's not in dimension d, it's the critical exponent in dimension d minus 1. And that's related sort of to the spaghetti picture, right? The spaghetti picture, the cross section lives in d minus 1 dimension. That's sort of where the d minus 1 comes from. Okay. And so to summarize the theorem again, so the only obstruction to the heuristics is a spaghetti-like degeneration. That's one way to summarize this theorem. Either the heuristics is true and everything is fine, or else you have spaghetti-like degeneration. If Polya's conjecture holds, then you know then this number is equal to 0, this critical exponent, and the second case does not appear, and we always have convergence in Hausdorff, sense to a unit measure ball. Okay, now if this critical exponent is strictly bigger than 1/2, then, right, I mean, if this is strictly bigger than 1/2, then you can find a gamma that satisfies this. In that sense, the problem of proving convergence to balls for all gamma positive is really equivalent to proving that this critical exponent is less or equal than 1/2. So, right, you really see the difference. And that, I mean, in some sense, it's bad news because, I mean, why do you study asymptotic problems? Well, you think because in an asymptotic limit, the things simplify. Things become easier. They're asymptotically simplified. Here, well, they simplified somewhat because from d dimension, we got down to dimension d minus 1, but we ended up with inequalities. These are universal inequalities, and they either hold or do not hold. But we sort of don't know. There is no parameter to play with anymore. Okay, and now what does this theorem have to do with the theorem that I had on the first slide? Well, that's easy. See, when you're in 2 dimensions, then you have to compute the critical Riesz exponent in 1 dimension, but in 1 dimension Polya holds, so therefore the second case does not occur. Similarly, when you're in dimension 3 and higher, then you can check that, and if gamma is greater than 1/2, then you see that you always, this thing always holds. So again, the bad case does not hold. So this theorem is really stronger than the theorem that I showed you in the first slide. On the first slide, I simply did not bother you with this dichotomy about this critical exponent. But the critical exponent is really what's going on and where you really see what's going on in the shape optimization problem. Now, there's one more main result. So this critical exponent, right, that appears there, and we would like to understand it better. And I already told you that from the Beresin-Liao inequalities and Kröger inequalities, we know that, well, we have these semiclassical inequalities when gamma is greater or equal than 1. So in particular, we have these inequalities for convex sets. We have them for any, but we have them in particular for convex sets. And therefore, the critical exponent for convex sets is greater or equal than 1. Now, here comes a result that's also in this newest paper, where we say that the critical exponent is strictly smaller than 1. Okay, so let me be precise. What I'm saying is the inequality with semiclassical constant, that's the constant that you see in the Weyl asymptotics, right? the inequality with that constant holds for all convex sets and all lambda for all gamma that are, well, a tiny little bit below 1. The tiny little bit depends only on the dimension and on your choice of boundary conditions. Okay? And so this is really the first result. I don't know, these Bayesian inequalities, they're like 50 years old or something. I think this is the first time that one could break this barrier of gamma equal to 1. See, why is gamma equal to 1 a barrier? That's because this function, as a function of, say, lambda, is a convex function. And both the Bayesian-Liao proofs and the Kröger proof really essentially use the convexity of that function. They really use gamma greater or equal than 1. Now, some years ago, we looked at the same problem in the presence of a constant magnetic field. Okay, you can ask for similar inequalities when you have a constant magnetic field. And the interesting thing is when you have a magnetic field, then you have the inequalities for gamma greater or equal than 1, and you do not have them for gamma less than 1. They immediately break down when you leave the convexity range. And so it could have been that even for this problem, that would have contradicted Polya, of course, I know, but nevertheless, we've seen Polya is not right when you have a constant magnetic field. Okay, so there are situations where the convexity really is crucial, and what we show here, that's the deeper meaning of this result, is that this convexity is not crucial. Now, of course, the question that you will ask me now is, what is this number? Or put differently, what is this epsilon? And unfortunately, I do not have a good answer to that. The answer that I can give you is that no compactness was used in the proof. So meaning, if you have time, you can look at these 150 pages and track every constant, every inequality. There's no compactness. You can really find every value. You have to make certain choices. When we optimize our parameters, you have to do that. But you can do it in principle. And then you would get a number. Now, we didn't do this because we expect that the number that comes out will be terribly small. So it's rather the conceptual value of the theorem that I think is important, that really that gamma equal to 1 is not a threshold, that at least for convex sets, you can go below. That's my opinion. But, it would be nice, now that we know that the result is true, it really would be nice if somebody could find a proof and get an explicit value. So that's, I think, an important open problem. And then when you read this, so here we had this, remember we had this second part where we have this spaghetti-like degeneration. Now, you can exclude I should perhaps go there. When I wrote this result here, I wrote gamma greater or equal than 1/2. Really, you can put there now gamma greater than 1/2 minus this magic epsilon, because that's sort of by what we improved this critical exponent. And I should also say, if you're interested, of course, we tried to do things, and we do have some results about, this is the inequality. And then we have the critical point where semiclassical constant changes to non-semiclassical constant. And at the critical value, we studied existence and compactness of minimizers and so on. So there we have something in our paper, but I don't want to do that now. Okay, so these were the first two results, or the only two results of this talk. And I want to spend the remaining time explaining you the ideas of how to prove them. And so there are two ideas that I want to get across. Okay, the first idea is uniform semiclassics, and the second idea is a partially semiclassical limit. Let me start with the first idea. Okay, uniform semiclassics for convex sets. Okay, this is about Weyl asymptotics, where we're sort of back to slide 1. Here I wrote down the Weyl asymptotics. And if you look these asymptotics up in any book, what you will see is sort of you will have a fixed set omega, and then there will be a proof what happens as lambda goes to infinity. Now, already in this discussion, we noticed that really there are two parameters in the game. There's the lambda that goes to infinity, and then there's the set omega that varies, right? Because omega is a minimizer, an almost minimizer. So omega also depends on lambda. And I cannot use the theorems from the book that say that set is fixed, lambda goes to infinity. But I need to take variations of omega into account, okay? And we already told you, I mean, this uniformity fails. I mean, these asymptotics are not uniform in as the set omega varies completely. But here we prove a theorem that it is a version of uniform semiclassics in the realm of convex sets. Let's go through that. So first observation, this holds for any gamma all the way down to 0. Secondly, it holds uniformly for any sets and any lambdas. There's nothing asymptotic about this bound. Now, on the left side of the inequality, we have the Riesz mean and the first two terms in the Weyl asymptotics. And on the right side, we have something. Well, what is the something? Well, first of all, we have the term that is essentially the second term. And now this is multiplied by something, by function f. The function is different in the Dirichlet case and in the Neumann case. Importantly, this function is applied to a dimensionless product, namely the in radius of the set and the square root of lambda. Semiclassics means that this dimensionless product goes to infinity. See, in your textbook proofs, omega is fixed, so R omega is fixed, so square root of lambda goes to infinity. That's the standard case. But now, what we allow is that omega changes, and the only thing that matters is that the product of the in radius with the square root of lambda, that this goes to infinity. And when you have this, then, well, what these functions are, f, is not important. The only thing that matters is that these expressions tend to 0 as this variable r omega times square root of lambda tends to infinity. So in other words, what this theorem tells you is semiclassics starts as soon as the in radius times the square root of lambda is much larger than 1. Right? So sort of you can think of 1 over square root of lambda, that's the Planck scale. So I mean, we can prove semiclassics down to sets that become very, very thin. The only thing you want is they don't become as thin as the Planck scale. You just need to, the sets still need to be much larger than the Planck scale. A multiple of the Planck scale needs to fit in. Okay, as soon as this is satisfied, you have, and of course you have convexity, then you have semiclassics. That's the meaning of this. Now that theorem requires quite a lot of work. And I've given talks about this recently. This was in one of these two papers. And I don't want to go really through the proof. I mean, there are several ingredients. In particular, we used all these tools from classical analysis, Tauberian theorems, Riesz interpolation, and so on. Combine that with certain heat asymptotics and so on. Anyway, for now, I want to just keep this as a black box. This is uniform semiclassics all the way down to the Planck scale. Let me show you an application of this. Remember, I told you that the critical exponent is smaller than 1. Let me prove that. Let me sketch the proof. There's one more idea that we need, but half of it is this uniform semiclassics theorem. Right? So this is the theorem that we want to prove. I focus on the Dirichlet case just to fix ideas. Neumann case, just turn around all inequalities, same proof. So because we have this semiclassical thing, Well, you have here this surface area times power of lambda is the same term. So here you have a constant, and here you have something that tends to 0 as this thing becomes large. So you only need to make sure that this term is smaller than this constant here, and you have the desired inequality. Put differently, what that says is for any gamma, no restriction, there's a constant such that if this product is large enough, then you have the inequality you want. Perfect. So this tells us we need to prove the inequality only for small lambdas or for small values of this product. Now, there's a very cheap argument that says that if you have the inequality for gamma equal to 1, then you get it even for gammas that are less than 1, but you have to pay a price, multiplicative error. Okay, and roughly speaking, this lambda here, so there's a capital lambda here and there's a little lambda, and this little lambda needs to be allowed to vary a little bit, but not too bad. Anyway, so what we will use is that if this gamma, right, so you extrapolate an inequality. And if you extrapolate only a tiny little bit, then the price you have to pay is arbitrarily small. Okay, good. So remember, we have proved the inequality for large lambda, so we still need to prove it for small lambda. Good. For small lambda, well, there was a price that we had to pay, but it's a tiny price. So let's see about that. So if we could gain here something at gamma equal to 1, then we'll be happy. And that's exactly what this lemma says. The lemma says that, so the lemma actually does not have a restriction. The lemma says that, you know, where was this? This was the inequality. Beresin-Liao told us when gamma is 1, then the inequality holds. But actually, we can improve it. We can improve it by a tiny little amount, something that's exponentially small in lambda, but we can improve it. And so this improvement helps to offset the loss that we made in this extrapolation argument. Okay, there's a little, so this is this lemma actually holds for arbitrary sets of finite measure, no convexity needed. What enters is the width of the set. You know, you ask yourself, what's the minimal distance of hyperplanes between which I can squeeze my set? And so it's this dimensionless product width times square root of lambda that enters. And for convex sets, the width and the inner radius are comparable. All right. Now, this requires some argument. And so in particular, what we use is a certain uncertainty principle due to Nassarov. It says something about if you know that the Fourier transform is supported in a finite set, what do you know about the function? Anyway, so this was just, I mean, I don't want to stress that point too much. I just wanted to give you one application of these semiclassics that are valid down to these values. I told you there were two ideas in the proof. That was idea number 1. Now here's idea number 2. That's what we call partially semiclassical limit. That's where we have to talk about these spaghetti-like degenerations. Okay? They could also be lasagne-like degenerations, right? Spaghetti-like, one direction is long. Lasagne, when you have one sheet of lasagne, you have two directions that are long and one that is thin. And in general, well, you can have many different lengths and behaviors, but only have a finite number of them. Okay, so here's how this goes. Take a convex bounded open set. Good. Now there's something called the John ellipsoid, and that's the unique maximum volume ellipsoid contained in omega. That thing exists. And it's an ellipsoid, and therefore it has semi-axes, d of them. That are, the semi-axes are orthogonal, but I guess I should say it's the length of the semi-axes, okay? So these give us the length scales. so forget John ellipsoid and so on. The important thing you want to do is you just want to associate d different length scales to your convex set. The smallest one, that's the in radius. That's sort of the smallest length scale that's in the picture. The largest length scale, that's the diameter. And in 2 dimensions, these 2 length scales describe convex sets, at least degenerations of convex sets. Now, when you are in 3 dimensions, you need 1 more length scale. And well, we take this additional length scale to be a length scale of a John ellipsoid. But what's more important than these particular numbers is their behavior as for along a sequence of convex sets. And so I say that such a sequence n degenerates if n length scales become super huge, while d minus n, the remaining d minus n, all remain comparable. That's the picture for my lasagne, right? For my lasagne, so n for the lasagne, n is equal to d minus, did I say that correctly? No, for my lasagne, n is equal to 1, right? So d minus 1 length scales. These are the length scales of the cross section of your spaghetti. They remain all comparable, whereas one direction becomes long. And the standard example that you can keep in mind is take a fixed set omega and multiply it simply by a cube or a ball that becomes huge. Okay, then n directions become huge, whereas d minus n sections remain bounded. Okay, now here's our theorem. That's the second main ingredient in this proof. Assume you have a sequence of positive numbers and of convex sets, bounded, of course, and you assume the following. You assume, first of all, that they n degenerate for some number n. We don't specify what n is. Okay. The smallest scale of these sets, right? Remember, the in radius, that's the smallest scale. That's comparable with 1 over square root of lambda. Okay. And then you have this trivial condition that the volume times lambda to the d goes to infinity. These are the conditions. And then we can compute, oh, right, okay. Then we look at these Riesz means normalized by their Weyl value, right? So this is the Weyl constant, and this is the term that you find in Weyl thing. And now we assume that this limit exists. You know that it's bounded from above and from below, so it certainly has a lim sup and a lim inf. And just take a sequence along which the lim sup exists or the lim inf exists, or any other sequence. So just assume that this thing exists. And then we can express it as something. We can express it in a sort of peculiar way. There's an integral dy over Rn, where remember n is the number of degenerating directions. Okay, and now, so you have a set, let me start reading here. You have a certain set omega star in Rd. Okay, now our Rd I write as a product of Rd minus 1 times Rn, Rd minus n times Rn. And now for each I slice, okay, for each fixed value of omega of y sits in Rn, I take the slice of omega star and I call that omega star y. That is now a set in d minus 1 dimension. And what I'm telling you is you have to look now at an eigenvalue problem, at a Riesz mean in dimension d minus n. I think n dimensions have disappeared. They went off to infinity. Okay, so you're left with d minus n dimensions. And in d minus n dimensions, you have to study a Riesz mean. However, look careful. The power of the Riesz mean has changed. We started with exponent gamma, and it went up to gamma plus n over 2. All right, and then what I've written is, well, the Weyl constant in the corresponding dimension with the corresponding exponent and the corresponding Lebesgue measure in this space in which we're living. And then you see I've multiplied and divided by the same quantity. You'll see that in a second where this comes from, why I did this. But that's the theorem. Well, that looks not really understandable, I imagine, at first sight. So let's look at it, the theorem in the simplest possible case. You know, that was the basic situation where we degenerate, right? When we just have a fixed set omega and we have this large cube. And then we look at, you know, this number, this, so L is now what's playing the role of J is now L, and L goes to infinity. And this lambda J, that's a fixed number mu. And I want to keep mu fixed. And that's comparable because if you look at the set here and compute its in radius, the in radius is essentially the in radius of little omega, right? Because, I mean, the long directions, they don't help you and don't hurt you. Okay, so in radius times the cutoff level is constant. That's our assumption. Good. L to infinity means that this assumption is satisfied. Good. And now here, see, for this problem, you can solve things explicitly, right? The eigenvalues are eigenvalues on your little omega times eigenvalues on this cube, on this big cube, which you can write out in sine and cosine. And you'll see that it doesn't really make a difference whether you use sine or cosine or just take periodic boundary conditions and get exponential by e to the I kx. Doesn't matter. But the point is, when you do the computation, right? I mean, the modes of the eigenvalues in this cube, they become semiclassical. So then you do the computation and you can write this trace as an integral over n-dimensional phase space where you still have to compute the quantum problem in omega. You really have the eigenvalues, but the other Laplacian, the Laplacian in the directions that you lose has disappeared. So that, as I said, I mean, you can look at this conceptually, or you can look at this just by hand playing with sines and cosines. And from here on, everything is easy because this the psi integral you can do. And then you see there's some algebra going on with these constants, how they behave. And what I'm trying to tell you is this thing here, once you believe that approximation, then you have this theorem. And so that was the model case. That was the model case where we have a cylinder, where we have a fixed cross section times something huge. And in the general situation, you don't have that. But, you know, the ordinary Weyl asymptotic proof that says that essentially we have that. We can cut along the super long, see, we have our spaghetti. The spaghetti is super long. We cut the spaghetti into pieces, say into 10 pieces or 10 or 100 pieces. But so that the length of the slices is always super large. Then essentially you reduce it to a constant cross section, and this is still large, and then you get these asymptotics by sort of looking at constant cross sections locally. Okay, that's roughly speaking the proof of the theorem. Now I tried to tell you, to explain you what this has to do for our shape optimization problem, but I guess in the interest of time, I'll skip that. And I come to my last essential slide, which gives you the proof of the main theorem, assuming these two ingredients. Okay, so let's assume that gamma is bigger than this number here. That means when, you know, and that's typo, actually, I apologize. This is d minus 1 here. Okay, now, right, when this number is less or equal than 1/2, then this is an empty restriction. Otherwise, it's the regime where we claim that we converge to balls. Okay, so let's take this sequence of minimizers or almost minimizers. Doesn't matter. Okay, good. First assertion is these sets do not well, in the language I used there, do not one degenerate. I mean, I just want to say that the in radius times square root of lambda j is equal to infinity. Okay, so even along the shortest direction of these sets, we can still fit more and more Planck lengths in, and therefore, according to our semiclassical limit, no, sorry, okay, good. So that's what we claim. Let's claim that. Why is it true? Assume the opposite was true. Assume that the lim sup here was, or the lim inf, say, was strictly finite. I mean, less than infinity. Okay, then we are in our partially semiclassic limit theorem. And we're in this theorem, right? That's exactly this assumption that holds. That one is easy. Okay, here we are. So we get this magic set omega star such that we have this identity. Now let's stare at this. Here I've written it again. That's the identity. See, here I have my problem in dimension d minus n. And what I'm claiming is that for this problem, the exponent, the new exponent for the new dimension is actually supercritical, meaning I do have the semiclassical constant there. And therefore I can bound this by 1. And then, you know, this is just Fubini, right? The d minus n dimensional measure of all the slices integrated along the parameter that you slice over gives just the total measure. So this is a probability measure, and then you get a bound by 1. You have to work a little bit harder. Unfortunately, we're not done yet, but it's, I mean, it requires work. But just to focus on the idea, well, your exponent here is really strictly bigger than the critical exponent in the corresponding dimension. And this you can upgrade to say that this is actually strictly less than 1. You cannot have equality in the semiclassical inequality. Okay? And then it's strictly less than 1. This is strictly less than 1. And that contradicts even to leading order the fact that you're an optimizer. Okay? So the contradiction has been reached, and we know now that this limit is greater than 0. But now that we know that the in radius times the square root of lambda goes to infinity, we can now apply our uniform semiclassics theorem. That says exactly all the way down to that quotient. I mean, as soon as this quotient goes to infinity, then we have semiclassics. Here they are. This is semiclassics for these sets. Now, what do we use? Now we use the optimizing property, just energetically, meaning, well, our set omega j is at least as good as a ball is, right? Because a ball is a valid competitor. So I write the same asymptotics down for the ball. Well, for the ball, the first term is the same. Here I might potentially see a difference. Here I got the surface area of my sequence, omega j. In the other, when I look at the competitor, the ball, I get the surface area of the ball. Now, because I'm an almost minimizer, I learn that I have an inequality. The surface area of my approximate minimizers is less or equal than the surface area of the ball. So in other words, my sequence omega j, remember they all are volume normalized. They are an optimizing sequence for the isoparametric problem. And then by standard facts about the isoparametric problem, I learned that they converge to balls in Hausdorff sense. That's the end of the proof. Okay, so you see I used the ingredients to the partially semiclassical limit and the uniform semiclassics to deduce that result. All right. And with this, I'm at the end of the talk. So once again, we've studied a shape optimization problem in an asymptotic regime. We proved convergence to balls. In dimension 2, it's unconditionally. In dimension 3 and higher, we have a condition, but it's a necessary and sufficient condition. So it's if and only if, and it depends on a certain eigenvalue inequality in dimension d-1. And that's all for today. Thank you very much for your attention. Thanks.
Thank you very much for the very nice talk, Rupert. We have time for questions now, and if you do have questions, please either ask them in the chat or unmute yourself and ask them directly to Rupert.
May I have a question?
Sure.
President Bloom.
Right.
Rupert, what do you think? How much of this or how little of this can be extended to variable coefficient second order operators?
Okay. It's an interesting question. Let's see. I mean, one thing is, of course, normalization, so that the argument works. If you have variable coefficients, your leading term sort of depends on the coefficients, right? It's sort of there's a volume there. So from that point of view, I'm not quite sure how to normalize or how to phrase the shape optimization problem. But if we dig deeper into the proof, these uniform semiclassics for convex sets, right? I mean, there is no asymptotics anymore. Here, it's sort of clear what the analog should be, and I would hope that theorems like this hold, at least for smooth variable coefficient operators. But even that case, I mean, one has to work, and so our proof uses very different techniques. There's some coherent states here, some heat kernel techniques. In each step, one would have to work a bit, and then. I mean, the idea, since we can deal with rough boundaries, dealing with rough coefficients might be possible as well. So, I mean, all the methods that are used sort of are built to minimize smoothness requirements. So, I mean, if you have C1 or continuous coefficients, it looks good. If one can go really to bounded measurable coefficients, then I guess one would to have a lot harder, and I'm not so sure.
Okay, to make the things more concrete, I think it might be interesting to consider the spherical Laplacian and the hyperbolical Laplacian.
Right. Okay. Okay. So this is a good exact. I mean, this is a very, very good question. I mean, even the asymptotic shape optimization problem should work, and in that case, I'm really very, very confident that it works for the operator on the sphere. But there I would use the particularities of the sphere to simplify questions.
Thank you, Rupert. There is a question in the chat. So the question is, do you have uniform asymptotics for the counting function instead of Riesz means with your method?
Okay, so I mean, the short answer is, I guess, no. But we have something that's good enough for some purposes. So I should say I skipped all results for gamma equal to 0, just to make life simpler. We do have the results that we do have a logarithm, the same logarithm that Courant got in 1920. However, we get the logarithm with the correct, I mean, the dependence is only on the in radius times the square root of lambda. So for all theorems for which you don't need the exact second order, I mean, there was an example of this argument here. This was only leading order, where it was only relevant that it was uniform with respect to the in radius. That works. So yes and no is the answer.
Thank you. I have perhaps one question myself. You mentioned implications of Polya conjecture, but if you could rule out the spaghetti-like degenerations, then you would presumably have everything up to, like, for all gamma bigger than 0. And then does it say something about the Polya conjecture?
Yes and no. So here in this question, really gamma 1/2 is the threshold. So if I could rule out spaghetti-like degeneration, I would prove that this critical exponent is less or equal than 1/2, which would be, I think, a big step towards at least Polier for convex sets, right? I mean, if anything of this sort of works, then it would be Polier for convex sets. And so excluding spaghetti-like degeneration would put this critical exponent less than 1/2. However, there are similar optimization problems where you have slight modification, where you optimize over finite disjoint unions of convex sets. And if we could solve that, then we could, and there we prove a similar theorem with a similar dichotomy. And if we could rule out that dichotomy, then we could go all the way down to Polier. Okay, so
you have Polier, or you have asymptotic Polier for large energies, or you have even for the first eigen.
No, it would be Polier.
Okay.
Polier for convex sets.
Yeah.
Okay, Polier for convex sets. Now, see, the point is sort of that because of the degeneration, the asymptotic parameter disappears. It becomes a uniform parameter.
Thank you.
And so there are in our paper, there are a couple more sort of equivalences that if Polier fails, then what must happen? So there would be certain sets that degenerate in a certain version and optimize. So we studied this in some detail. Thanks for pointing that out. Thanks.
Does anyone else have a question or comment? If not, let's thank Rupert again. Thank you very much. And we will reconvene next week for a talk by Weyl, who will speak about small eigenvalues of many-cusped hyperbolic surfaces. Meanwhile, until then, have a great week.
Thank you. Bye-bye.
Thanks a lot, Rupert.
Thank you.